All right, folks, this is the final lecture on single loop circuits, and it's definitely the most complicated. So I'm calling it real batteries aren't perfect, and you can see that right there. They are catching on fire. So this lecture is fire. Okay, this is what we've done so far. We've pretended like batteries are perfect, where it is only giving you energy in joules per coulomb. I'm not sure why I had that, why I have that picture, but let's just say you have a 9-volt battery. That means it's giving you 9 joules per coulomb, and it's only giving away energy, and then this light bulb is using that energy. I just made that number up. I don't know that that's going to match these numbers here. But the battery is giving energy to the electrons, and then the electrons convert their kinetic energy to light in the light bulb. Okay, so that's what we've done so far. Pretty straightforward. Not surprisingly, just like your laptop gets a little warm, not as much as they used to like 10 or 15 years ago, but in a real world battery, the electrons are not only going to lose some energy in the appliance, but they're actually going to lose some energy inside the battery. So how do you know what's what? There's 2 little knobs. They're unfortunately not going to be color-coded because I can't Xerox in color, but those represent the terminals of the battery. So like when you see a 9-volt battery, these little things plus and minus, or when you see your AA batteries, one side is positive and one side is negative. Okay, so whatever's between the 2 dots is inside the battery. And then what you see is the battery is going to give 9 joules to every coulomb that goes through, yay. But then it's going to take some energy away, because for the electron to physically travel through the battery, it's going to have some collisions and turn some energy into heat. Okay. So that's what's going on, but you can see it's still a single loop circuit. It's just that one of the resistors is inside the battery. So we're going to be using a lot of the same formulas. You just got to be careful about whether you're talking about inside the battery or outside the battery. And we're going to see there's 2 different voltages. What you think you're getting, 9 volts, and what you really get. Okay, so give you a couple of, I don't love this definition, but I didn't make it up. All right, so to make things challenging, instead of calling it the ideal voltage, like the 9 volts, it's called the electromotive force, and I hate that because it's not a force. So I'm not going to use that term, but if you see a problem from a textbook or working with a tutor or find problems online, you might see that electromotive force, and its symbol is like curly QE. I find that confusing. We don't need that. Okay, so I'm going to call it the ideal voltage. This is the voltage if there were no energy lost in the battery. In other words, this is the voltage that it says it is, 9 volts, 1.5 volts. I have no idea what, I don't think that's Thomas, whatever. I have no idea what the heck that engine is doing in there. Okay, so the actual voltage is called the terminal voltage because it's the actual voltage you would read across the terminal. These are called battery terminals. The positive and the negative are the battery terminals. Okay, so the actual voltage is the terminal voltage, and I'm going kind of fast so that you're like, what's all this going on? You can see the formula and say, oh, okay, this is really not that complicated. All right, so this is kind of like, it costs you $90 for a concert, but 10 of that is a service charge. So you get an $80 concert, but you had to pay $90 for it. Okay. Or you buy a certain amount of energy of gas, but some of that energy just goes out the tailpipe. It doesn't give you kinetic energy. It generates heat. Okay. So just, hopefully that makes sense. Okay. This is the formula. You will get this formula. So TV does not stand for television. It stands for terminal voltage. that is not the 9 volts, but whatever it is, something less than 9 volts. E, this is supposed to be a curlicue E, but I think I redid all my worksheets so that it says IV for ideal voltage, because I think that just makes more sense. Okay, so terminal voltage is the voltage you really get. That's what you get, the $80 concert. The ideal voltage is what the battery, what we said before, the 9 volts. Clearly, what you get is less, so we're going to subtract some stuff. And what we're going to subtract is the voltage, the joules per coulomb, that it costs you to get through the battery. Just like it costs you joules per coulomb to get through a resistor, it's going to cost you some energy to get out the battery. And yesterday we learned what delta V, the formula for delta V is I times R. There's only one current, so we don't have to think about that. I make this a lowercase r because in general, the resistance inside the battery, unless it's a really, really bad battery, is really small. Like this is 0.2 ohms. So it tends to be much smaller than what you're hooking up to it. So I made that a lowercase r so that made more sense. Okay, you will get that formula, but you need to know what is what. Okay, so hopefully that makes sense. This is what you want, and it's equal to what you hoped you got minus some stuff, and they all have the units of voltage. Okay, don't panic. While this can be tricky, it is really a more challenging, but it is still a single loop circuit. Whew. Okay, so far, all of that background was just to help you understand this equation. So if this equation kind of makes sense, yay, you're in a good spot. Okay, now the second formula should also hopefully make sense. Since not all the energy will be useful, some of it is literally wasted, right? Your laptop gets hot. You don't want your laptop to get hot. You want it, to do calculations and show you cool physics videos. What we're going to do, because I think it's a really important skill and a good, just good number sense, we're going to calculate the efficiency of the circuit. I will also give you this formula. So the efficiency is, and you can just write it as lowercase e if you want, we'll know that it doesn't mean electron, is the ratio of two things. So for the concert, just to start with something concrete, it was what you get. I got an $80 concert over what it cost you. What did it cost you? It cost you $90 unless you bought it from a scalper, in which case it was even less efficient. But it's just a ratio. So whatever the numerator and the denominator are have to have the same units to write it as a percent. So this would be 0.8 repeating, and then you multiply by 100. So that concert was 88.8 repeating percent efficient. 88.8% of the money that you spent went to the concert. The rest of it went to processing fees. Okay, so back to the formula. The efficiency is the useful wattage, so maybe like the light, over the total wattage, which would generally be, okay, well, I got some light and some heat, and I didn't really want the heat. So the denominator is always going to be bigger than the numerator. Otherwise, it means you're getting something for nothing. Okay, so it's useful wattage over total wattage, or depending on what you have on your paper, right? Do you use what you have already? Useful energy over total energy. And I'm sorry that is so, like, those words are so weird. It was before I knew how to make fractions in this program called LaTeX. But anyway, moral of the story is it's a ratio. Numerator and denominator have to have the same units, and this is always going to be less than 1, right? We got 0.8 repeating. Okay, so two new formulas. terminal voltage, and efficiency. All right, let's see how we can apply that. All right, so question A says find the current because there's only one. So I is V over R tote. And the voltage is 9 volts, but the resistance is 10 plus 0.2 or 10.2 ohms, and that gives you 0.882 amps. Okay, so I've got 9, I'm giving away 9 joules per second, but I lose some energy inside the battery and I lose some energy outside the battery, and it doesn't really matter where it is. I'm going to divide by that because that's going to, both of those things are going to slow the electrons down, which is going to reduce the current. Okay, question B. Find the terminal voltage of the battery. So terminal voltage equals ideal voltage minus IR. This is what we want. What's the ideal? Well, I thought I had a 9-volt battery. The more current you have, the more you're going to lose, because the more current, the more collisions you're going to have, the more energy is lost to heat. So terminal voltage is 9 volts minus 0.176. So it's not a ton in this case. Again, it depends. The more current you have, the more the less efficient this is. Okay, so you actually only really have an 8.82 volt battery. And that's why the next, sorry about that, the next lab we're going to do, let's see if Control-Z works. Yeah, the next lab we're going to do is going to be a virtual lab, because if we used a real battery and you were trying to make predictions and measurement, you would think you would have a 9-volt battery and you'd really only have an 8.82 volt battery, and you'd get, you know, the numbers would be off and you might be frustrated. Okay, question C, find the wattage of the bulb, kind of a review question. So maybe you can try this on your own and pause the video and check back. The wattage of the bulb is I squared R. And you're only going to use the 10 ohm because you want to know how bright the bulb is. You don't want to know how much heat is generated by the battery. So that's why it's R individual. So we're going to take the current and we're going to square it, and we're going to multiply that by 10 ohms, and we get 7.78 watts. Okay, and then D, find the rate at which the battery is generating heat. Okay, rate, I'm not trying to, deliberately confuse you, but we don't tend to say what's the we tend to say what's the wattage of the light bulb or an appliance. We don't tend to say what's the wattage of the battery. We tend to say what's the rate at which it's generating heat, but that's just a fancy word for saying wattage, because watts is a rate. It's a joule per second. Okay, so don't be confused by the difference in terminology. So we're still going to use I squared R, but the R we're going to use is only the 0.2. So the battery is making 0.156 joules of energy of heat per second. Okay, and then the last question is find the efficiency of the circuit. And so efficiency is going to be some ratio. Generally, it is some kind of useful over some kind of total, making sure that you have the same units. All right, what did I want? I wanted light. How much light did I get? I got 7.78 joules of light every second. what did it cost me in the same units to get that light? Well, I had to pay for the light, right? I got that. But I also got 0.156 joules per second of heat. So it's going to be 7.78 over 7.94. So that is 0.979. And I want you, technically that's not wrong, but I don't like that. I would like you to write it as a percent because I think that has that more meaning. Because 0.979 could be, it doesn't necessarily indicate that it's a ratio, right? It could be 0.979, could be the coefficient of friction or what. Like, if you write it as a percent, then it is clear that you are talking about a ratio, in my opinion. Okay, so it is basically about 98% efficient. Which is why when like you were doing the open short complete lab, you know, the elements weren't getting super hot because for the most part, they're not going to get super hot. Okay. So just quickly, I think this is the last slide. Just quickly to review, there's still only one current, but you've got to include all the resistance. So 10 plus 0.2. There's a new formula for terminal voltage. You should be able to check your work. Clearly, what you really get is going to be less than what's listed. And then you've got power inside the battery and power outside the battery. I thought maybe I was going to say one more thing. Oh, yeah. What this is, the last thing is this light bulb, this 10 ohm light bulb, is the fact that you can think of this circuit in two ways. Although this is the best way, this is really what's going on. But as far as the light bulb is concerned, it's kind of like it has an 8.82 perfect battery all to itself. So that's kind of what the terminal voltage means, is instead of having a less perfect 9-volt battery, you have a perfect 8.82 battery, 8.82 volt battery to generate the same amount of light. Okay, so that's what that kind of means. I don't love that. If it helps it make you understand what that means, that's fine. But I don't love that because you don't really have a perfect battery. You have a battery that's generating heat inside, not a whole lot. All right, hope that makes sense, and I hope to make video answers for the worksheet so you can have more explanations if you need it. So thank you for listening, and sorry you missed class, and I will see you another time in class.